So when we graph the family of solutions, we're going to get a whole series of solutions that kind of follow this kind of shape. Okay, and if this differential equation is going to give us the slopes to all those pieces. Okay, so I can actually use this differential equation to generate a bunch of slope pieces like I did here. dy by dx equals negative 4xy squared. So I can choose a point at 1, 1. Sorry, x is 0, y is 1. And I plug it into there, I get a slope of 0. Okay, so, and that's true there. Okay, if I choose a point at, 1, x is 1, y is 1, I'm going to get a slope of negative 4. Okay, so it's going to have a slope of negative 4 here. At negative 1, positive 1 here, I'm going to get a slope of positive 4, okay, through there. And what I can actually do is generate a whole bunch of these pieces of slope. And if I just draw on all these different points all across this whole graph, all these little slope segments, what ends up happening is you end up being able to see generally how the graphs, the family of solutions should be looking, the shapes of those families of solutions. And this is something called a slope field. Okay, so I just did a couple here, but if I were to do a whole bunch of them, okay, you get a whole field that looks like this. So you have all these little slope segments that are calculated using the original differential equation. Because remember, the differential equation is the derivative, so calculate slope. So we can calculate these slope pieces here. Okay, and these are called slope fields. And if you take a look at the slope field, when you look at the field, you get a general idea what this shape of the graphs are going to look like. And here on the right hand side, we see all the different solutions, possible solutions, depending on where the graph goes through, okay? Depending on the initial condition, or the plus c. So this is very useful to get an idea of what the graph looks like when we get, especially when we get differential equations that cannot be solved. Okay, if we have a differential equation that cannot be solved, at least we get a look at an idea of what this graph's going to look like. And in fact, if we know an initial condition on the y function, what we can do is then take a point, let's say the initial condition is that point there, and we can use that point and we can actually just kind of start following the slope field and seeing that there's a graph that kind of looks like that. And let's say there's a point here on this graph. Well, it's pointing towards this. And it looks like it's kind of going up in this direction. It's kind of pointing down here, like that. Okay. And if it went through that initial point, or that initial point, we get these different solutions. And these would represent the different plus c solutions. And we can actually, even though we can't actually solve this differential equation, if we have the derivative and we know where a point on the original y function is, we could potentially just follow this slope field, and at least we have an idea what this graph is going to look like. And that's what's going on here. These are actually solved differential equations, but even if we can't solve it, at the very least we start getting an idea of what the function is going to look like, or the shape of the function. Okay? But in general, the slope field will give us the solution to the family of solutions, all the possible plus c value solutions that we can get from solving that differential equation. And sometimes we can actually solve them and come up with the actual graph. Sometimes we just have the slope field and we just have to estimate what that function is going to look like based on following the slope field. So if we want to find that solution to a specific function like we did here, we just know, if we know the position and we can actually solve for the plus c, we can solve the differential equation and find the plus c, we can get the specific curve. But if we can't do that, we can at least trace out the curve based on using the slope segments. Okay, this is the idea behind slope fields. So when we have a differential equation, we can generate a slope field. Now, obviously, we wouldn't generate a whole field because that would take way too long. But this is very easily done by computers now. But what we want to be able to do is at least find the slope sections to given different coordinates. So here, I've been given the derivative. The slope function is y over x. Okay, so if I have y over x, what I can do is I can take these x and y coordinates and draw slope sections. For example, at this point here, 4 over 5 up, okay, it's going to be 4 over 5. So I've got a slope kind of like that. At this point here, it's 2 over 3 up, or slope is 2/3. Okay, so it's a little less steep. Okay, it's kind of hard to draw, but again, it's just an estimate. Let's say that's 2/3 there. At x is 1, y is 0. Okay, that is going to be a vertical. Anything y is 0, we're going to get a vertical tangent. Okay, here x is 2, y is -3. It's the same slope, but positive here. Okay, sorry, negative. Here x is 4, y is -5. So it's a little bit steeper like this. It's essentially symmetrical. Okay, it's going to look kind of like that. So we end up getting these. We should be able to, we could have a whole field of this, but that would take a long time. But we can at least find slope sections at any given point by just plugging into the slope equation. So we also want to solve this general solution. So if I solve this, I'm going to separate and integrate. Okay, so when I separate and integrate this, integrate this side, I get y squared over 2 equals x squared over 2 plus c. I'm going to say that x squared minus y squared equals, and let's move the plus c to the other side. So times 2, so it's going to be -2c. So basically this, when I solve this differential equation, this is an equation of a hyperbola. Okay, with a trans, depending on the c, it could be trans x or trans y. If c is positive, it's trans y. If c is negative, it's trans x. So you can see that, yeah, that would generate, okay, this is a hyperbola, yeah. This slope field is indicating that it could be a hyperbola, okay. So what about this one here? We have the differential equation, okay, so we're going to calculate the slope field. We're going to generate a slope field by calculating slopes. So plugging in these coordinates, 1, 1, so we get slope of 2, y is 0, x is 1, we get a slope of 1, y is -1, x is 1, we get a slope of 0. Here we're going to get a slope of 0. Y is 0, x is -1, so we're going to get a slope of negative. And y is 1, x is -1, so we get a slope of 2 like this. So there's our slope field. Okay, this is not the whole field, we're just sketching slope segments. But if we continue doing that, we can generate a whole field. But we can also solve this differential equation. So because this one is a solvable differential equation, it makes it a little bit easier. So we're going to end up with dy over 1 plus y is equal to dx over x. Integrate both sides. Okay, I want to get rid of the log, so I'm going to put the plus c inside the log. So it's going to be 1 plus y equals log, I'm going to make that kx. Okay, so basically what I've just said is c is equal to log k, and then I use log rules to put that k into the log. Okay, so then drop the logs, y equals kx minus 1. So basically this is going to generate linear equations of different slopes depending on where my x and y is. So if x is, let's say x is 1, y is 0, okay, x is 1, y is 0, k would be 1. Okay, so then we have slope of 1 And this gives us the linear equation of y equals negative x minus 1. So that's going to be that line there. So we're going to get a whole series of linear equations that go through those different points. Okay? Okay. Oh, this one here is actually asking us to find the actual particular solution. So let's do that. So f of negative 1, okay, is equal to 1. So this one here, we're going to do it through that point. It looks like it's going to have a slope of 2. So if I plug in y equals 1, x equals negative 1. Okay, so we're going to solve for the slope here. So we get 2 equals negative k equals negative 2. So then my particular solution becomes y equals negative 2x minus 1. And that is going to be that line right there. Okay, and that's the solution that goes to that particular point of negative 1, positive 1. Okay, and our slope field kind of indicates that that's in fact true. Okay, we actually found the slope from the derivative, and we actually found the slope from the actual function, from the solution to the function. So they both correspond to each other.